Okay, good morning. So we're going to start our class now. All right, 1 second. Okay, so today we're going to keep talking about approximation algorithms. Okay, so we're going to look at a few problems today. So the first problem we're looking at is, wait, what is this? Not sure what this is. Okay, I don't know what that is. Okay, so the first problem we're looking at is this very famous problem called the traveling salesman problem. Okay, so sorry, how do I get rid of this? Okay, yeah, it's the traveling salesman problem. Okay, so this is actually one of the most well-studied problems in combinatorial optimization and operations research, and it has a lot of applications. So today we're going to look at basically the best known approximation for this problem, okay, which is a 1.5 approximation algorithm. So what's kind of interesting about this algorithm is that this algorithm was proposed almost 50 years ago. Okay, and yet, during all this time, there's not been any improvement on this algorithm. I mean, there's a slight caveat to that. Okay, so like in the last few years, there's been a very, very tiny improvement on the algorithm. Okay, but essentially, it's been the best algorithm for the last 50 years. And so this kind of shows how hard it is to come up with good algorithmic ideas, right? Okay, so anyways, let's first define the problem. So we're given a complete graph, complete weighted graph. Okay, so for example, in this picture below, we have an edge between every pair of vertices. Okay, this graph is undirected, so we can go in either direction. Okay, but all the edges have weights on them. And what we want to do is to create a cycle that goes through every city, or every one of these nodes. So I'm going to call these cities, I'm going to call these nodes cities sometimes. Okay, so then here we have, how many do we have? We have 8 nodes, and so we need to have a length 8 cycle that goes through each node exactly once. And our goal is to make sure that this cycle has the minimum total weight, right? Because all of these edges are weighted, so any cycle has a, oh, the slides are not changing. I see, all right, so can you guys, so I have like 3 lines of text right here. Can you guys see the third line where I'm saying the goal is to find a cycle with minimum total weight? You cannot see it. Okay, I used to not have any problems with these, with the internet connection, but, so guys, for the people who cannot see the slides, what are you seeing right now? Are you seeing like the title page, or are you seeing the first page with this picture? It's the title page. Okay. Can you try to log in again or something? So I haven't had this problem before, so I'm not really sure what to do. Can you try logging out and then coming back in? Okay, all right. Let's see, I don't have anything weird with my internet connection right now. Let's see. So yeah, I don't have this thing. You can reshare the screen. All right, let me try that. Okay, yeah. Okay, so 1 second. Let me stop the screen sharing and then reshare. Okay, I'll stop this. Okay, yeah, sorry about this. And then I have to reshare. Okay. Okay, so I think I'm, oh no, it's still not happening. Okay, so I am sharing my screen right now. Can you guys see the second page with the picture? Okay, all right, so hopefully we don't have any more problems with that. Yeah, okay, yeah, sorry about that. If there are more connection problems, just let me know, okay. All right, so as I was saying, so in this TSP problem, we have this complete weighted graph. And we're trying to find a cycle that goes through all of the nodes in the graph exactly once, right? And we want to make sure the cycle has the minimum total weight, right? Where the total weight is simply the sum of all of the edge weights in the cycle. Okay, all right, so this problem actually has a lot of real-world applications. Okay, so the name kind of implies that it comes from, let's say, a salesperson that wants to go through all of these cities. Right? But he wants to make sure that he takes the shortest path possible. Okay, and in practice, this situation comes up quite a bit Because if you think about companies like Amazon or Taobao or something, right? They need to deliver things. Okay, they have a bunch of delivery trucks, right? So they need to make sure that their trucks go to all the points where people have ordered products, right? But they want to make sure their trucks take the minimum total route. Okay, so this is a real-world application of this problem. So in practice, you might add some additional constraints. So for example, you might have, some of these edges might be directed because you have like one-way streets or something. Okay, or sometimes you might want to prioritize certain sites because those people paid more for their deliveries or something like that. Okay, so you can add sort of different variations onto this basic problem, but the heart of the problem is this traveling salesman problem. Okay, so all right. Okay, let me maximize my screen here. All right, so so for example, this would be one example of a cycle that we might find. Okay, and this cycle might not have the minimum total weight. And so, in fact, we are trying to find possibly a different cycle with the minimum possible weight. Okay, now the TSP problem is actually NP hard. Okay, and furthermore, when you try to solve this problem, you need to make some assumptions. And the reason is that if you don't make any assumptions about the problem, so for example, if you allow the weights in the graph to be arbitrary, okay, then it's not even possible to approximate this problem. Okay, so it's NP hard to approximate if the weights are arbitrary. So today we're going to see like a 1.5 approximation. Okay, but if you don't make any assumptions, then you can't even get like a 10 approximation or a 100 approximation or even like a billion approximation. Okay, so that means that even if you try to just find a solution which is only 1 billion times as large as the minimum possible solution, it is still NP hard to do that if you don't make any assumptions. Okay, all right, so we need to make various assumptions, and there are many different types of assumptions because, as I said, this TSP problem is very well studied, and different people are going to make different assumptions. Okay. So today we're going to consider a very natural and reasonable assumption, which is the metric assumption. Okay, so basically we're going to assume that our graph satisfies the triangle inequality. Okay, so what that means is, for example, if you have 3 points over here, 3 nodes, okay, then the triangle inequality just says that if you go directly from the node P to R, okay, that distance is no more than the distance if you take a detour from P to Q and then to R. Okay, so basically it's better to go straight towards a destination and not take any detours. Okay, that's what the triangle inequality says. And so this is the assumption that we're going to have for this graph. Okay. Now, in practice, there are certain situations where you do not have the triangle inequality. Okay, so for example, if these edges are like roads, right, then maybe right now somehow you have like lots of traffic on this road, on the road from P to R. Okay, so maybe it takes you 10 minutes to cross that road. Okay, whereas for the other 2 roads, right, maybe you don't have too much traffic, so somehow it's actually faster to go through the other, to take that detour through Q. Okay, so it is possible in real-world situations to violate this triangle inequality. Okay, however, for our problem, we're going to assume that this property is satisfied. Because again, if you don't assume this, then you end up not being able to do anything. You can't solve this problem at all. Okay. All right. So so this problem is called metric TSP because with the triangle inequality, the distances satisfy a metric. Right. And in this case, we can get a 1.5 approximation algorithm. All right, so before we look at the 1.5 approximation, we're going to start by looking at a simpler 2 approximation algorithm first. Okay, so this algorithm finds a solution which is at most 2 times the minimum possible solution. And these 2 algorithms, the 2 approximation and the 1.5, okay, so they're actually quite similar. Okay, so by looking at the 2 approximation first, we see the key ideas, and then we can add sort of one more nice idea on top of that and get a 1.5 approximation. Okay, so for the 2 approximation, so the steps are kind of like weird the first time you see them. Okay, but I'll just tell you what the steps are, and then later I'll give you some examples and intuition about why this is a good thing to do. Okay, so what we're going to do is the first thing we're going to do is to construct a minimum spanning tree on the graph. Okay, so let's call that minimum spanning tree T. And we can do that using any efficient algorithm, for example, Prim's algorithm or Kruskal's algorithm. Okay, and then after we have this minimum spanning tree, we're going to do a depth-first traversal to visit all of the vertices in T. Okay, and this DFS can start from any arbitrary node. Okay, and then after that, so after we form this depth-first traversal, we're going to somehow convert this DFS traversal into a cycle, which does not visit any vertices, revisit any vertices. Okay, so the DFS might revisit some vertices, but we're going to convert it to a cycle somehow, which I'll show you, which does not revisit any vertices. And then the cycle is going to be our TSP tour. Okay, and this cycle is guaranteed to be a 2 approximation. Okay, so let's do an example of this. Okay, so here we're going to start with the graph on the upper left in this A thing. Okay, so this is a complete weighted graph. And in B, we're going to compute a minimum spanning tree. Okay, yeah. And then in C, all right, so let me just show you all the steps here. So then in C, we are going to do a DFS traversal on this minimum spanning tree. Okay, and in this case, we're going to start our DFS at node A, but you can actually start anywhere. Okay, and so the DFS is basically just going to, it's going to walk around this entire tree. Okay, so imagine that you're like a little person over here, right? And so let's say you've got your left hand over here and your right hand over here, okay? And so you're just going to sort of walk along this tree, okay? So just imagine that you're walking along this tree, and as you walk, you always keep your left hand on the tree. Okay, so here's your right hand, here's your left hand, and you just always keep it on the tree. And then, anyways, so that way you can walk all the way around the tree. Okay, so now we get this cycle, but the problem with this cycle is that it revisits certain vertices, right? So for example, here, we're gonna go, we go to B once, and then we go back to B, right? And then we go to H, and then again we go back to B. Okay, now in the TSP, we're not allowed to revisit vertices. Okay, so then what we do in this case is we do this procedure called shortcutting, okay, which means that if you're about to revisit a vertex, okay, so like here, if you just follow the DFS, you're going to revisit B, okay, but in that case, we're just going to take a shortcut and just skip over the B, okay, because we don't want to revisit B, so we'll just skip over B and visit the next unvisited vertex, which is H, okay, and then likewise when you get to H, if you follow the DFS, you would go back to B and then to A, right? You would revisit B and A. But we don't want to do that, so we're just going to take a shortcut directly from H to the next unvisited vertex, which is going to be D. Okay, so we're going to go straight to D. Okay, and then you can go to E, because we've never been to E before, right? And then you can go to F, and then from F, you do not want to go back to E, so you're going to go to the next unvisited vertex, which is G, right, and so on. And so, so this is how you go from this DFS, which revisits vertices, to this other tour shown in D, which does not revisit any vertex. Okay, and then this thing is the output of the algorithm. And now this tour or this cycle is not necessarily the shortest cycle. So in fact, for this example, the shortest cycle would be something like this. Okay. However, our cycle is at most 2 times as long as the minimum cycle. Okay, so that's the algorithm. Are there any questions about this? Okay, so I just want to talk a bit more about this shortcutting procedure in case it's not that clear. Okay, so what we're trying to do again is to go from this DFS tour, which can revisit certain vertices, and we just want to make sure that we do not revisit any vertices, because the TSP requires that you do not revisit vertices. Okay, yeah. So so in this shortcutting procedure, right, we can just write out in the DFS the sequence of nodes that we visit, right? So we first go to A, and then B, and then C, and then B, and then H, and so on. So I've just written out the entire order of that of these visits, okay? And now in the sequence, you just look for whenever you go back to a node that you've already visited, right? So for example, the second B in red, okay? Well, we've already visited B, so this is a revisit to B, okay? And likewise, this other B is also a revisit to B, okay? And this A is a revisit to A, okay? So then whenever you get one of these revisits, you just take it out, okay? You just completely cut it out, okay? And then so what you're left with is like A, B, C, H, D, E, F, G, A, okay? And then as you can see, in the final tour that we output, we go through A, B, C, H, D, E, F, G, A. Okay, so that's the shortcutting procedure. Okay, does that make sense? Okay, all right. So now we can try to we can prove that that we have a 2 approximation. Okay, so we need to use a few lemmas. So the first lemma is that in this shortcutting procedure, okay, what's very important about the shortcutting procedure is that it does not increase the length of the DFS tour. Okay, so imagine that you have this DFS tour right now, and it's got some certain length. Okay, so then what we do is we apply all these shortcuts, right? We, for example, add this shortcut, we add this shortcut, this one, and then this one. Okay, and the claim is that when you add any of these shortcuts, you do not increase the length of the cycle. Okay, so if the original DFS had a length of, let's say, 10, okay, then after you add all these shortcuts, you have a length at most 10. Okay. And the reason this is true is because let's just look at one shortcut. Okay, so for example, when you shortcut directly from C to H. Okay, now originally in the DFS, you go from C to B to H. Okay, and now you go directly from directly from C to H. Okay. And now this is where we use this metric assumption. Right, so we assume that the distances satisfy the triangle inequality, and that means that when you directly go from C to H, when you do the shortcut, okay, this is not longer than when you take this detour from C to B to H. Okay, so the CH distance is no more than CB plus BH. And so that means that when you add this detour, you're not increasing your length. When you add the shortcut, you're not increasing your length. Okay, and likewise, when you add this shortcut, right? Then originally you had to take these detours. Okay, and the detours can only be longer than the shortcut. Right, so once you add the shortcut, you're not going to increase the length. Okay, so this is where we again, this is why we need this triangle inequality to show that as you shortcut, you don't increase the length. Okay. Yeah, so in fact, this is the first lemma that we're trying to prove, okay? So this lemma just formally states what I just showed you, which is that if H here is the shortcut of the original DFS, which I'm going to call T prime, okay? Then the C of H here is just going to be the length of H, okay? The cost of H, okay? Then the cost of H is no more than the cost of the DFS. Okay, and the reason is simply that we did some shortcuts, we skipped some intermediate nodes, and so by the triangle inequality, right, you never make your path longer when you skip over these nodes. Okay, and this applies to all of our shortcuts, and so in the end, the shortcut path is not longer than the DFS path. Okay, all right, so now, so then once we have this, we're basically, we can now prove the approximation ratio. Okay, so now let's prove that we have a 2 approximation. Okay, so to do this, suppose H star here is the optimal TSP for the original problem. Okay, so we want to compare our cost to H star's cost. Okay. Now, the first thing is that, so H star is some sort of cycle like this. Okay, and so now if you delete an edge from H star, okay, so let's say you, let me draw it differently. So H star is some sort of cycle, right? And if you delete any edge from H star, okay, so let's say you delete this one, right? Then you get a spanning tree, okay? Because what you're left with is this chain over here. But we know that the chain goes through all of the nodes because the original TSP tour goes through all of the nodes, okay? And so, so this chain here is not, it's kind of a degenerate tree. I mean, it doesn't have any branching. Okay, but it's still a spanning tree. And so therefore, what we know is that So remember, the first thing that we do is to compute a minimum spanning tree in our algorithm. Okay, so we're going to compute this MSTT. And so because we have the minimum spanning tree, then we know that our minimum spanning tree has lower cost, or has no higher cost than than the tree we get by deleting an edge. Okay, and this tree that you get from deleting an edge, right? This is going to be only shorter than the original TSP tour, right? Because you just simply took out an edge. And so this means that our tree, right, the cost of our tree is going to be no more than the cost of the original TSP. Okay, so this is important. Our MST is cheaper than the original TSP, than the optimal TSP. Okay. All right, now the next thing that we did after this MST is that we did this depth-first traversal on the MST. Okay, and what that depth-first traversal does is it's going to cross every edge in the MST twice. Okay, so let's go back to these to this picture over here, right? So if you look at this DFS over here, right, you see that every edge in the MST gets used twice. Okay, so we go down here, right? And then we're going to reuse the CB edge. Right? And likewise, we're going to reuse the BH edge and the AB edge and so on. Okay, so you can see that every edge gets used exactly twice in the depth-first traversal. Okay, so and so that means that when you do this DFS and get T prime, then the cost of T prime is exactly 2 times the cost of the MST because you traverse every edge twice. Okay. All right, so next, after we did this DFS and got T prime, we did the shortcutting procedure, and then we got this graph H. Okay. Now, first of all, you notice that H, so H is actually a Hamiltonian cycle, or meaning that it visits all of the vertices, and then it visits all the vertices exactly once, and also ends where it started. Okay, because the DFS itself visits all of the vertices. Right? So if we go back to the picture, we can see that the DFS visits all of the vertices, right? And then when you do the shortcutting procedure, you still visit all the vertices, okay? But each vertex you only visit once. And also you go back to where you started, right? We started A and we ended A. Okay, so therefore this shortcut graph is going to be a Hamiltonian cycle. And by our previous lemma, the total cost of the shortcut graph is no more than the cost of the DFS. Okay? All right, and now we put everything together. So we have that our shortcut graph, which is what we output, right? So this is this cost is no more than the original DFS, and the DFS, right, is not more than 2 times the cost of the MST, right? And the MST, which is this T over here, right, that cost is no more than the cost of the optimal TSP. Okay, so therefore our tour, right, our Hamiltonian cycle is no more than 2 times the cost of the optimal TSP. Okay, so that is the proof. Any questions about this? Okay, all right. Okay, so now we're going to improve this 2 approximation to a 1.5 approximation. Okay, and to do that, we need a few more concepts. So we've actually talked about these things before. Okay, so we talked about matchings and Euler cycles, and we need to use these in our in this improved algorithm. Okay, so let me just remind you what these things are. So first of all, a matching in a graph, okay? So this is just a set of edges, a subset of the edges in the graph, okay? But the edges are not allowed to touch each other, okay? So for example, for example, in this example over here, right, in this graph over here, right, all of the red edges, those form a matching, okay? And none of the red edges touch each other, okay? And a perfect matching, so we actually need more than a matching, we need a perfect matching. So this is a matching where all the vertices are part of, which includes all of the vertices. Okay, so you can see that all of the vertices in this graph are part of some matching. Okay, so for example, this vertex is, so we selected these red edges, right? So this vertex is part of this edge, right? This vertex is part of this edge, and so on. Okay, so that's a perfect matching. Okay, so next we need to talk about Euler tour of a graph. Okay, so an Euler tour of a graph is a path that starts and ends at the same vertex. Okay, and it has to visit every edge once. Okay, so this is different from the our previous requirement to visit every vertex once. Okay, so the Euler tour has to visit every edge once. Whereas for the TSP, we require a Hamiltonian tour which visits every vertex once. Okay, so it might seem like a small difference to visit every edge versus every vertex. Okay, but actually this is a huge difference. Because Euler tours are actually very easy to compute. Okay, so in fact, we have a way to characterize when a graph has an Euler tour. Okay, so some graphs might not have an Euler tour. It might not be possible to visit every edge once. Okay, but we have an exact characterization of which graphs have Eulerian tours. Okay, and yeah, so this is a theorem due to Euler, who is like sort of the founding father of graph theory, basically. Okay, so he's a Swiss mathematician. From like 200 years ago. So the property is that if you have a graph where all of the vertices have even degree, okay, so a graph has an Euler tour if and only if all of the vertices have even degree. Okay, so for example, in this graph over here, right, you can check that all the vertices have even degree. So this is guaranteed to have an Euler tour. Okay, so let's see what the Euler tour is. I always forget how to do this one. So what do? We think we do something like this. Okay. Okay, excellent. All right, yeah. Okay, so there we go. Okay, so if you follow this red tour over here, right, you see that we go through every vertex. Every edge. Okay, yeah. All right. So we have an easy way to check whether a graph has an Euler tour. And actually, there's also an efficient algorithm to find an Euler tour, if it's possible. Okay, so so this problem, the Euler tour problem, is actually pretty easy. On the other hand, as soon as you change things to visiting all the vertices once, okay, then you require Hamiltonian tours, and now this is NP complete. Okay, yeah. So for some reason, so I don't have the best intuition for this. Once you go from edges to vertices, the problem becomes much harder. Okay, but anyways, so that's what these matchings and Euler tours are. Okay, so now we're going to use them in the 3/2 approximation. So this algorithm is by Christofides. Okay, and so again, we need to assume the triangle inequality. So this 3/2 approximation is actually pretty similar to the 2 approximation. Okay, so for example, the first thing that we do for the 3/2 approximation is that we also compute a minimum spanning tree, T, on the graph. Okay, all right. So suppose you have some sort of graph, right? So I'm not showing the entire graph. So the entire graph is like a complete graph. Okay, I'm just showing the MST on the graph. Okay, and now in this MST, you might have some nodes with odd degree. Okay, so for example, if you look at all of these red nodes, right? Like this red node over here has degree 1, right? This has degree 3, and so on. Okay, so we're going to pick out all of the nodes with odd degree, and you're going to call that set of nodes V prime. Okay, and now we're going to construct a perfect matching on V prime. Okay, in fact, we're going to construct a minimum cost perfect matching M on V prime. Okay, so if you look at all of these red nodes, okay, so the perfect matching means that we need to match, it means that all of these red nodes need to be part of this matching. Okay, so you see that here we're selecting these red edges. Okay, and now remember that this graph here is sitting inside of a complete graph, right? I'm not drawing the complete graph, but actually you should imagine that all pairs of nodes are connected. Okay. And so therefore you can form any so therefore you can form a matching on these nodes, right? And then later on, I'll prove to you that it's possible to form a perfect matching. Okay, and furthermore, you want the cost of this matching to be minimum. Okay, so the cost here is just the sum of all of these edge lengths. Okay, you want that to be minimum. And it is possible to find these minimum cost perfect matchings. Okay, so there are efficient algorithms for doing this. So just assume that we can do this this step, and we have this matching M. Okay, all right. So next, what we're going to do is we're going to add M, add these red edges, okay, to the original MST. Okay, so here you see that we have the original MST, and then you add these 3 red edges. Okay, and that way you're going to get a new graph, and we're going to call that T prime. Okay, and so notice that T prime allows you to double some edges. Okay, so for example here, right, the MST itself already had an edge between these 2 red nodes. Okay, and the matching also adds another edge between these 2 red nodes. Okay, so we allow this to happen. This is okay for us. Okay, and now in this graph, in this T prime, okay, so this is T prime over here, right? We're going to find an Euler tour. Okay, we're going to find an Euler tour T double prime. So I'll show you later why it's guaranteed that we can find an Euler tour in T prime. Okay, and the final thing that we do is we take this Euler tour T double prime, right, and we shortcut it. Okay, so shortcut is exactly the procedure we talked about earlier. So we're going to shortcut T double prime, and that is going to produce a Hamiltonian cycle H. And that's going to be our output. Okay? All right, so again, the algorithm is that we start with a with a minimum spanning tree. Right? You find all the odd degree vertices, and then on these vertices, you compute a minimum cost perfect matching. You add that matching to your MST, to your minimum spanning tree. Okay? And then in that new graph, right, you're going to find an Euler tour, and then you're going to shortcut that Euler tour, and you get a Hamiltonian cycle, and that's your output. Okay? Any questions about this? Okay. All right. So before I prove why this is a 1.5 approximation, okay, let's first sort of compare the 2 approximation and the 1.5 approximation to sort of see why this new algorithm is better than the previous one, right? Why we get 1.5 instead of 2, okay? So the basic idea for the 2 approximation is that, so in both cases, in both the 2 approximation and the 1.5, we had to find an Euler tour, okay? Where Euler tour is, it goes through all the edges, right? Because if you go back to the 2 approximation, right, you see that this thing, okay, this is also an Euler tour, okay, where here we imagine that we double all the edges. Okay, so imagine that for every edge you have, we're supposed to have undirected edges. Okay, but now imagine that for every undirected edge, you make it directed in both directions. Okay, so for every edge, you just double the edge, right? And then you see that the depth first search, in that case, the depth first search is exactly an Euler tour on this doubled TSP. On this doubled MST. Sorry. Okay, on the doubled MST. All right. So therefore, the depth first search has 2 times the cost of the MST. Okay, and that's ultimately where the 2 approximation comes from, because the doubled graph has 2 times the cost of the MST. Okay, and now the reason that Christofides works better is because it doesn't just double your MST. Okay. Instead, it adds this matching to the MST. Okay. And then in this new graph, which is the MST plus the matching, it finds an Euler tour in that graph. Okay. And what you can show is that the graph, which is the MST plus the matching, okay, this is going to be shorter than doubling the MST. Okay. In fact, what we're going to show is that the MST plus the matching is going to be at most 1.5 times the cost of the MST. Okay, and that's where the 1.5 approximation comes from. Okay, we don't double the MST, we just find something which is 1.5 times as large, and so in the end, we're going to get a 1.5 approximation. Okay, yeah, so that's the basic idea for why the Christofides works well. Okay, all right, so now let's do the proof. Okay, all right, so the first thing we need to prove is that this T prime. Okay, so the T prime is the MST plus the perfect matching. Okay, so we need to prove that this actually has an Euler tour. Okay, And so to prove this, what we have is, so the first claim is that if you look at V prime, which is a set of odd degree vertices, okay, then there are an even number of vertices in V prime. Okay? Yeah, so for example, if you go back to the graph over here, right, you see that you have 6 odd degree vertices. Okay, and the claim is that we always have an even number of odd degree vertices. Okay? And the reason for this is that if you look at a graph, okay, and you add up the degrees of all the nodes, okay, then you're going to end up counting every edge twice. And so that means that sum of all the degrees is going to be an even number. Okay. And so now, so if you look at all the nodes, then some of the nodes have even degree, some of the nodes have odd degree. Okay. So so if you only look at the odd degree nodes, and now suppose for contradiction, there's actually an odd number of odd degree nodes. Then if you add together all their degrees, you get an odd number. Right? Because you have an odd number of odd degree nodes, so you add together all their degrees, you get an odd number. Okay? And now you add that to the degrees of all the even nodes, and so that's going to be an even number. Okay? So then altogether you would get an odd number. Okay? So if you have an odd number of odd degree vertices, then the total degree would be odd, which is not true, which is a contradiction. So therefore you have to have an even number of odd degree vertices. Okay, yeah, so, yeah. All right, and now, so since you know the odd degree vertices, you have an even number of them, right? And because these vertices, V prime, remember they're sitting inside of a complete graph, right? I didn't draw the complete graph, but they are sitting inside of a complete graph. And so therefore, there's a perfect matching on V prime in this complete graph. Okay, like if you have 6 vertices, it's always possible to find 3 edges, which includes all 6 vertices. Okay, and furthermore, you can find the minimum cost perfect matching efficiently using, for example, there's an algorithm called the Blossom algorithm. Okay, so you can find these in polynomial time. Okay, and now now if you look at the matching, okay, the degree of every node in the matching is odd. Okay, so for example, if you go back to the matching over here, right, you see that all the nodes in the matching have degree 1. Okay, and now if you add the edges in the matching to the original MST, then all of the nodes in the all the nodes in the new graph are going to have even degree. Okay, so for example, you see here you had a node which used to have odd degree. Okay, but if you add the matching edge, right, then that's going to increase the degree of this guy by 1. And so now this guy is going to have an even degree. Okay. Likewise, this guy used to have an odd degree, right? But once you add the matching edge, right, then his degree increases by 1, and so now he's got an even degree. Okay. Same thing over here, right? This guy used to have degree 3, and then now he's got degree 4. Okay. So once you add the matching, then in the new graph, which is this T prime graph, right, all of the nodes have even degree. Okay. And now, we have that Euler theorem, which says that if you have a graph where all the nodes have even degree, then it's guaranteed that you have an Euler tour. Okay, so that's why we are guaranteed that you can find this Euler tour. Okay, so that proves this this lemma over here. Does that make sense? Any questions about this? Okay. All right. So okay. So next, we have this other lemma, which says that okay. So if you so let's again we want to compare to the optimal TSP. Okay. So let's call that H prime. And also we found this minimum cost perfect matching, right? And so let's let M be the cost of that minimum cost perfect matching. Okay. And now the claim is that the matching's cost is no more than twice the cost of the optimal TSP. Okay. All right. So the reason for this is that now let's just focus on a subset of all the nodes. Okay. So let's only focus on the odd degree nodes, these V prime nodes. Okay. And so suppose H prime is an optimal TSP only on these V prime nodes, not on all the nodes V, only on V prime. Okay. Then, of course, the cost of H prime is going to be no more than the cost of H star. Okay? Because H star is an optimal TSP on all the vertices, and H prime is an optimal TSP on a subset of the vertices. Okay, so therefore H prime's cost is not going to be more than H star's cost. Okay, now in this picture over here, these purple nodes are supposed to represent V prime. Okay, so these are supposed to be the odd degree vertices. Okay, right, now H prime here, right, this is going to be a cycle on V prime. Right, H prime is a TSP, so by definition, it's a cycle. Okay, and also remember that V prime has an even number of nodes. Okay, and so that means that H prime consists of two matchings. Okay, the two matchings are the odd edges and the even edges. Okay, so for example, here you see that we have how many? We have 8 edges in our cycle. Okay, so this is supposed to be H prime over here. We have 8 edges. So if you take edges 1, 3, 5, 7, right, that is going to be a matching, right? And then if you take edges 2, 4, 6, 8, that's also a matching. Okay, both of those are perfect matchings. Okay, right, and now whichever one of those matchings is cheaper, let's call that guy M prime, or sorry, the cost of that thing, let's call it M prime. Okay, that's of course going to be no more than half of the cost of H prime. Okay, because H prime is just a cycle, and then M prime is just half of this. Okay, the cheaper half. So it's going to be no more than half the cost, right? And we know that H prime, right? H prime is not going to cost more than H star. Okay, and so therefore this M prime is going to be at most half the cost of H star. Okay, and the final step is that M prime over here is just some sort of matching on V prime. Okay, however, our M is the minimum cost matching on V prime. And so therefore our M is going to be no more than M prime. Okay, which is also no more than half of H star. Okay, so that shows that our matching's cost is at most half the cost of the TSP, optimal TSP. Okay, any questions about this? Okay, so I think we're supposed to take a break, but let me just finish this. Okay, so I've got about like 3 minutes left, or I just need like 3 minutes to finish up this proof. Okay, and then we can take the break after that. Okay, so now we can prove the the 3/2 approximation ratio. Okay. Okay, so let's let H be the TSP that we output. Okay, and let's let H star be the optimal TSP. Okay, so we're trying to show that our output is at most 3/2 the cost of H star. Okay, so over here I just sort of rewrote the algorithm just to sort of remind you what's happening in the algorithm. Okay, right now, so the steps are that first of all, the first step we do is to compute this MST. Okay, so the MST is going to have cost at most the optimal TSP cost. Okay, remember that's because if you take the optimal TSP and you take out an edge, then you get a spanning tree, and that spanning tree can only be more expensive than our minimum spanning tree. Right, and now and now T prime, which is the MST plus the matching. Okay, well, we just said that the matching's cost is at most half of the cost of the optimal TSP. Okay, and the MST is also at most the cost of the optimal TSP. Okay, so therefore this matching plus the MST is going to be at most 3/2 the cost of the optimal TSP. Okay, and the final thing we did was that we took this T prime here, right, and then you shortcut it. Okay, so we did the shortcut to get this thing H over here. Okay, and again, by the triangle inequality, we know that when you shortcut, you're not going to increase the length. Okay, so therefore our H is going to be no more than T prime's cost. Okay, and oops, right, and so now you put everything together and you get that our cycle's cost is no more than 3/2 the optimal TSP cost. Okay, so that's the proof. Any questions about this? Okay, so all right. So before we finish with TSP, I'll just mention a few other things about this. Okay, so I said that this 1.5 approximation, this has been the best thing for like the past 40, 50 years. Okay, so actually in the past I don't know, like 2-3 years or something, there's been a tiny improvement to this approximation factor. Okay, so they improved it by like a factor of something like 10 to the negative 30th or something. Okay, so they got something like a 1.4999999 approximation as opposed to 1.5. Okay, I mean, I don't know that algorithm. It's actually very complicated. Okay, but I think the basic idea for that algorithm is still to basically follow the plan of Christofides. Okay, which is to start with an MST, right, and then add something to the MST. Okay, so here we added this minimum cost perfect matching, and this 1.499 approximation adds something else. Okay, and then that something else is somehow slightly cheaper than the minimum cost perfect matching. Right, the perfect matching has a cost which is half the optimal TSP cost, and the thing that they add is like 0.499999 times the optimal TSP cost. Okay, and that thing that they add is like very, very complicated. Okay, but still, the basic idea of that algorithm is still similar to Christofides. Okay, yeah. Okay, so that's one thing. Something else is that I mentioned there are many variations to TSP. Okay, so one interesting variation is something like Euclidean TSP, where all of the points in the TSP represent points in Euclidean space. Okay, so that's one possible variation. And then also you could consider planar TSP, where planar means that the graph that you have, okay, is planar, meaning that none of the edges cross each other. Okay, so for example, all right. For example, this graph over here. Okay, the top graph is planar because none of the edges cross each other, whereas the bottom graph here is not planar because you have crossing edges. Okay. So in these special situations, like the planar situation or the Euclidean situation, you can actually do much better than 1.5 approximation. Okay, so in fact, you can get a 1 plus epsilon approximation for any positive epsilon. Okay, so you can get something like a 1.00001 approximation if you want. In these special settings. Okay. Your runtime is going to increase as you make epsilon smaller. So if you're trying to make epsilon 0, let's say, okay, so you try to compute the optimal TSP, then your running time is going to blow up to infinity. Okay, but for any fixed epsilon, you can compute a 1 plus epsilon approximation in polynomial time if you make these special assumptions. Right. And there are many other variations to TSP. So as I said, it's one of the most widely studied problems. Okay, any questions about anything? All right, so in that case, I guess we're supposed to take a break. So let's not take too long of a break. Let's just break till what is the right, so actually our break is supposed to happen right now. Great. Okay, so then let's take a 8-minute break. Okay, so let's come back at 11:10, right, and then we have more stuff to talk about. Okay, and if you have questions, you can ask during the break. Hi, yeah, so there's a question about the project. So I think we'll release the project this week. Okay, so then, and you have, when does the semester end? I think it ends sometime like in like mid-June or something, right? So you have like a month to do the project. Okay, yeah. Oh. Okay, yeah, so let's continue with our class. Yeah, and again, somebody was asking about the project. So the project will be released this week. And yeah, so you have like a month to do the project. Okay, and it's not like a very complicated project. Okay, it involves some sort of programming, but the problems that you're trying to solve are similar to the problems, to the homework problems. Okay, so it's not like like a super complicated project. Okay, all right, so we're going to continue with the lecture. So we're going to move on to a new problem called the K-center problem. Okay, all right, so for the K-center problem, suppose you have a city with a bunch of houses, like in this picture. And now you're going to build some, let's say, grocery stores. Okay, and you want to make sure that everybody is close to some grocery store so that people can do their shopping quickly. Okay, and so the question is, where should you put these grocery stores so that every house is close to some grocery store? Okay, so for example, if you put the grocery stores here, okay, then we assume that every house is going to go to the grocery store which is closest to it. Okay, so for example, this house over here, right, this is going to go to this store and not this other store. Okay, so every house will go to the nearest grocery store, right? And so if you put the stores in these places, okay, then the longest distance that anybody has to travel is something like, well, maybe this distance. Okay, right? So this is the farthest distance that any person is from their nearest grocery store. Okay, and our goal for the K-center problem is that we get to put K of these stores anywhere we want. Okay, and we want to minimize this maximum distance that somebody has to pay. Okay, so we want to minimize the maximum distance. Okay, so a bit more formally, so we can say something like this. Okay, so first of all, we're going to call these houses, we're going to call them sites. Okay, and the stores, we're going to call them centers. Okay? And we're going to assume that every site is going to be mapped to its nearest center. Okay, so if you have a site S, and then if you have a set of centers C, okay, then the distance of the site from all of the centers is going to be, we're going to look through all the centers and find which one is closest to S. And that's going to be the distance of S from these centers. And our goal is to make sure that all of these sites are close to some center, to its nearest center. Okay, and so the way to write that is, so for each S, right, for each site, we map it to its closest center. And now you want to look at all of the sites, and you want to see which site is the farthest from its center. Okay, so you're going to maximize over all of the sites, and you're going to look at this quantity over here. Okay, and we're going to call this quantity the radius of all of these centers. Okay, so yeah. Okay, and we want to minimize the radius. Okay, is that clear? Yeah, so we need to figure out where to put the centers to minimize the radius. Okay, so you can kind of think of this as like a clustering problem. Okay, where you get to you're going to make K clusters. Okay, so you get to pick the centers of these clusters, right? The locations of the cluster centers, and you want to pick these locations so that the sort of the size of each cluster. Okay, the maximum size of a cluster, you want to minimize that. Okay, right? And the question is, where do you want to put these cluster centers? Okay. Does that make sense? Any questions about this problem? Okay, and we're gonna, again, we need some assumptions. Okay, otherwise this problem is hard to solve. So the assumption is that the distances satisfy the triangle inequality. Okay, so just like for TSP, and so that means that, for example, if you take these three houses, right, then, you know, if you add up these sort of the detour, Q plus P, right, then that's going to be, that can only be more than the direct path from the first house to the other house. Okay. Right, so yeah, so this is the problem that we're trying to solve, and we're going to look at a algorithm, so it's going to be a two-approximation algorithm for this problem. Okay, so this problem, the K-center problem is NP-complete. Okay, so we need to look for an approximation, and this algorithm called Gonzalez's algorithm is a two-approximation. Okay, so it's actually based on a very simple idea. It's kind of like a greedy idea. Okay, so what's going to happen in this algorithm is that we're going to add these centers one by one. Okay, so in total, you want to add k centers, but we're going to be adding them one by one. And at every point, when you're going to add the next center, okay, what you're going to look for is which site is the farthest away from all of the current centers. Okay, so whichever site is the farthest away from all of the current centers, then that site is the thing that's making our radius large. Right, so remember, the radius is like the maximum distance of any site from its closest center. Okay? So if you have a site which is very far away from all of the current centers, then that site is causing our radius to be large. Okay, so that site is hurting us. Okay, so then what we'll do is we'll just make the distance for that site be small. Okay, and to do that, we're just going to put a center directly on that site. Okay, if you put a center directly on that site, then that site's distance now becomes 0. So it's not going to hurt us anymore. Okay, so that's the idea. Okay, so yeah, in pictures, suppose we're adding these centers one by one. So the centers are these red squares. Okay, so we've currently added one center, and now you have a node which is very far from all of our centers, from our current center. Okay, so this node I circled, right? This guy's hurting us. Okay, he's got a large radius, and so therefore for the next center, we'll just put it directly on that node. Okay, and so now his radius is going to be small. Okay, it's going to be 0, in fact. So he's not going to hurt us anymore. Okay, right. So that's the idea for Gonzalez's algorithm, right? It's kind of a greedy algorithm where whoever's causing the most problems, you just go fix that guy. Okay, and then you do this k times. Okay, yeah. Oh, right. And notice that we do allow putting a center directly on the same location as a site. Okay, so you can put the centers anywhere. Yeah. Okay, so more concretely, so this is the algorithm. So C is going to be the set of centers we output, right? And we're going to add them one by one. So initially it's going to be empty, right? And we're just going to repeat k times because we want to add k centers. So each time we're going to choose a site S which has the maximum distance from all of our current centers. Okay, and then you're just going to put a center directly on S. And then you just do that k times, and that's your centers. Okay, yeah, so it's a very simple algorithm, but it's actually kind of tricky. It's interesting how to analyze this algorithm. Okay, so I think this proof is actually quite interesting. Okay, so let's prove that we get a 2 approximation for this algorithm. Okay, so first of all, let's let C be the set of centers that we output. Okay, and let's let R be the radius of this of the set of centers. Okay, so again, R equals we look through all of the sites, and for each site you find the closest center, right? And so whichever one of those distances is largest, that is R. Okay, now, so we need some lemmas. So the first lemma is that if you take any 2 centers that we computed, okay, their distance has to be at least R. Okay, so pictorially, yeah, if you take, let's say C and C prime here, okay, these 2 red dots, okay, so let's say these are 2 centers that we output, okay, then the claim is that their distance has to be at least R. Okay. And so, so this is going to be a proof by contradiction. Okay, so let's assume that their distance is less than R. Okay. And now, first of all, we know that there is some point S which is at distance at least R from all of the centers. Okay, because if all of the points are within distance R from all the centers, then the radius would be less than R. Okay, right? The radius is defined as you look through all of the all the sites. Right, and then you pick the closest center. Okay, so if all these values here are less than R, then the radius itself would be less than R. Okay, but the radius is R, and so that means that there has to be a point which is at least distance R from all of the centers. Okay, so for example, this S point here. Okay, right, and now so we're assuming by contradiction that that C and C prime have distance less than R. Okay, and so so remember that we added these centers one by one. Okay, so suppose that we added C first and then later added C prime. Let's just assume that. Okay, right. And now if the distance between C and C prime is less than R, okay, then in the iteration where you added C prime, right, remember, the way that we pick these centers is that you pick a site which is the farthest away from all of your current centers. Okay, and now here, S is distance at least R from our current center. Right, so C is one of our current centers, and S is at least distance R from C. Right, and on the other hand, C prime is less than distance R from C. Okay, and so that means that in the iteration where you added the C prime, okay, you actually would not add C prime because C prime is too close to C. Okay, instead, you would add S or some other node, which is more than distance R from C. Okay, but you definitely would not add C prime. Okay, but that's a contradiction because C prime is one of these centers that we added. Okay, and so that means that C prime has to be at least distance R from C. Okay, yeah. Does that make sense? Any questions about this? Okay, so so as a corollary to this lemma, we can say that there are k plus 1 points which are mutually at distance r from each other, at least distance r. Okay, so so there are k plus 1 points where if you take any pair of these points, okay, then their distance is at least r. Okay, that's a corollary to this. Okay, and the reason is simply that we have k centers. Okay, and we just said that all of the centers are distance r from each other. Okay, so that's k of the out of the k plus 1 points. And then also we said that there has to be this point S, which is at distance at least r from all of the centers, right? Because otherwise C's radius would be less than r. Okay, yeah, so there's this so there's this additional point S, which is also at distance at least r from all the centers. And so you add it to these k centers. And so now we have k plus 1 points, which are all at least distance r from each other. Okay, so that's the yeah. So let's call this set of k plus 1 points. Let's call that D. Okay, so now we're going to prove another lemma. So this is well, okay, yeah. So the so now let's look at the optimal cover C prime. Okay, and suppose the C prime has a radius R prime. Okay, and so the all right, and so the lemma is that suppose our radius, our cover, has our radius, suppose it's more than 2 times the optimal radius. Okay, we're trying to show this is not true. Okay, so but we're going to use proof by contradiction. And so first, we're going to assume that our radius is more than 2 times the optimal radius. Okay, then in that case, for every one of these points in D, so there are k plus 1 points in D, right? Then the claim is that there's a corresponding point C prime, which is part of the optimal cover. Okay, and the C prime corresponds to D. And furthermore, all of these C primes are different. Okay, so so what's happening here is that so suppose we have like 2 points in D. Okay, so these 2 red points, suppose those are the points in D. Okay, so this lemma is saying that for every one of these D points, we have another optimal center, right? So these are these stars over here, right? And these correspond to these D points. Okay, and furthermore, each of these optimal points corresponds to just 1 D point. Okay, so for example, you don't have this point corresponding to 2 different D points. You just have like a 1 D corresponds to 1 D point. Okay, and so ultimately where this is going to lead is that remember we said that D has k plus 1 points in it, right? And so that means that if every one of these D points has a corresponding optimal point from C star, right? Then C star also has to have k plus 1 points, at least k plus 1 points. Okay, because for every D point you have a unique C star point which maps to which corresponds to that D point. Okay, but now that would be a contradiction because well we have we have k plus 1 points in D. Okay, but we only have k points in C star, right? Because C star is a k cover, so there are only k points in there. Okay, yeah. So if you assume that our radius is more than twice the optimal radius, then you get this conclusion, but this would be a contradiction. Okay, so that's ultimately going to be our proof. But let's first prove this lemma. Okay, does this lemma make sense? Any questions about this? Okay, all right, so to prove this, what we're going to do is we're going to draw a circle of radius r divided by 2. Okay, so r is our algorithm's radius. we're going to draw a circle of radius r divided by 2 around each center that we output. Okay, so like this. Okay. And now there has to be a optimal center. Okay, there has to be some C star in each of these circles. Okay, because because this let's see, C because C can be at most distance r star away from its nearest center, nearest optimal center. Okay, so so we have this optimal cover over here, right? And it's got a radius of r star, and what that means is that every node, every site has to be within distance r star from some of these centers in C star. Okay, so in particular, our center, the C, right, it can be at most distance r star away from the nearest optimal center. Okay, right, and then also since we drew this ball of radius r over 2, and we assume that r is larger than 2 times r star, right, then this ball actually covers this distance r star over here. Right, so C is within distance r star from some optimal center. Okay, and r star is less than r over 2, and so therefore this optimal center has to fall within this circle around around one of our centers. Okay, yeah, and so that so for every one of our centers, okay, so for all centers in D, okay, we can find one of these optimal centers. Okay, and it's got to lie strictly within the circle, right? Because the circle has radius which is larger than r star, and the distance between our center and the optimal center is at most r star. So therefore, these optimal centers strictly lie within the within these circles. Okay, and now the thing is that these circles actually do not touch each other. Okay, because we have this other lemma which says that all of these centers are all of our centers are at least distance r from each other, right? That was one of our earlier lemmas. And now we drew these circles of radius r over 2 around all of our centers. And so these circles actually do not touch each other except possibly at one point. Okay? And so that means that because these optimal centers are sitting strictly within these circles, then each of these optimal centers is different from each other. Okay, so for example, you could not have like, C1 prime, that cannot correspond to both C1 and to C2, because in that case, because C1 prime strictly lies within this C1 circle, right? And so that C1 circle does not intersect the C2 circle, except possibly at one point. Okay. All right, does that make sense? Right, so all of these optimal centers, corresponding to all of our centers, all of these optimal centers are different. Oops. Okay, and that's what we're trying to prove, right? We're trying to prove for every one of our centers, you can find a corresponding unique optimal center. Okay, all right, so, okay, so then once we have this, then we can just finish up the proof, okay? So the, so we're going to compare our output, this Gonzalez's output, right, to the optimal output. And the claim is that our radius is no more than 2 times the optimal radius. Okay, and so the reason is because it's what I said. Okay, it's that reasoning by contradiction is that if you assume our radius is more than 2 times the optimal radius, then by the previous lemma, right, for every one of our centers, there's a unique optimal center. Okay. However, we know that we have k plus 1 points in our set D. Or sorry, not one of our centers. Every one of our points in D. Okay, so there are k plus 1 points in D, which includes k centers and then one more point. Okay, so we have k plus 1 points in D, and so that would mean that there are k plus 1 points in C star, which is a contradiction because C star is a k center. Okay, and so that means that our radius is at most 2 times the optimal radius. Okay, any questions about this algorithm? Okay, so so the next, we're going to move on to another problem. So this is kind of different from the previous two problems, which were kind of sort of geometric or graph theoretic. Okay, so next we're going to look at the problem of scheduling in a parallel computing setting. Okay, so scheduling algorithms are actually used all over the place, right? So if you have an operating system like in your computer or your phone, right, all of that depends on scheduling to run efficiently. Okay. And in particular, all of these things that we have nowadays, like like laptops and cell phones, they're all parallel. Okay, basically any system that you any computing system that you interact with is probably parallel in some way. Okay, and so parallel just means that you have multiple processors in the system, and so therefore at any time point you can run multiple tasks. Okay, and when you have all of these processors, and when you have a bunch of processors and a bunch of tasks, then you have the scheduling problem, which is to decide which tasks are going to run on which processors, and also what time they're going to run at. Okay, so that's the scheduling problem. Right? Take a bunch of tasks and then map them onto processors, and then also for each processor, when it gets a set of tasks, you need to figure out which order to execute those tasks and at what time to execute them. Okay. Yeah. So right, and when you decide, so when you're scheduling these tasks, you can be trying to optimize for many different objectives. Okay, so for example, one thing is you can try to optimize throughput. Right, throughput is like the total amount of work that you do at any time point. Right, you can try to maximize that, but you might also try to maximize something else like fairness. Okay, you might want to make sure no processor does too much work. Right, and when you optimize for fairness, so these objectives might actually conflict with each other. Right, so in other words, the highest throughput schedule might actually not be a very fair schedule. Okay. Right, and other objectives are like you might want to minimize energy usage when you schedule. Okay, so there are many possible objectives. However, the one that we're going to look at today is simply latency. Okay, meaning that if you have a set of tasks, right, you just want to finish all of them as soon as possible. Okay, you don't care about anything else. You just want to finish all of them as soon as possible. Okay, yeah, and when we look at so this latency is actually called makespan. Okay, in the scheduling literature, this is called makespan. So we're going to be looking at makespan scheduling. Okay. And there are many variations even on makespan scheduling, okay, because you can assume many different things about the system. And so we're going to look at a very simple version of the scheduling problem. Okay, so in our problem, we're going to assume that you have n jobs, and the jobs are independent, meaning that they can be done in any order. Okay, there are no precedence constraints among the jobs. And furthermore, all of the jobs, each job can be done on any machine. So we have a bunch of parallel machines, and you can run any job on any machine. Okay. So the only difference between the jobs is that they have different sizes, where the size of a job is just how much time you need to run the job. Okay. All right. And also, we assume that you have m processors. Okay. And again, we're going to assume a very simple model where all of the processors have the same speed. Okay. And furthermore, each processor can only do one job at a time. And now our task is to assign these n jobs to the m processors. Okay. And when you do that, we want to minimize the makespan. Okay. So the makespan is when the final processor finishes all of its jobs, and you just want to minimize that. Okay. So for example, if you have these 8 jobs over here, right, and let's say that you have these 4 processors. Okay, then if you assign them in this, if you schedule them in this way, then the makespan is when the last processor finishes. So it's just when P2 finishes. And you want to schedule things in a way which minimizes the makespan, which corresponds to finishing everything as quickly as possible. Okay. All right. Now, before we solve this problem, I just want to mention that this is a very simple model for scheduling. Okay. Because, for example, we're assuming that all the jobs do not have any dependencies on each other. Okay, well, in practice, jobs often have dependencies, so that you might have to do one job before you can do some other job. Okay. And also, in practice, the jobs maybe you can't do them on any machine. Okay, maybe like, for example, if you want to run a program, it needs some sort of some data or some special subroutine, and that data might only be on certain computers. Okay, so there's restrictions on where you can place different jobs. Okay, but in our setting, we don't assume any restrictions. Okay. And also, you can imagine that you have different types of processors, and so they run at different speeds. Okay, so you could have like CPUs and GPUs and FPGAs and whatever, right? And they can run at different speeds. Okay, but again, in our setting, we just assume that everything runs at the same speed. And then one other big assumption that big thing that we're ignoring is communication between the jobs. Okay, so when you finish one job, maybe it needs to give some data to some other job. Okay, so that's some sort of communication between these jobs, and this communication is often very expensive. Okay, because it often takes more time to like transfer data than to do the computation. Okay, so communication actually has a large cost, but we are completely ignoring communication here. Okay. Yeah, and so this is a highly simplified model, okay, of scheduling. Okay, but nevertheless, it's useful because it can still show us some ideas which we can use in more complicated settings, more realistic settings. Okay. And in addition, even though we're making all of these simplifying assumptions, okay, this problem is still NP-complete, right? So even like the simplest version of scheduling is NP-complete. And so the more complicated versions are sort of even harder to solve. Okay. All right, so the first thing is let's prove that minimizing the make-span is NP-complete. Okay, because it's such a simple problem, you might think that it's actually possible to solve this optimally. Okay. All right, now the decision version of scheduling is clearly in NP. Okay, decision version is something like, I give you a target make-span. Okay, you got to finish within 10 minutes. Can you do that? Okay, yes or no. Okay, and that's obviously within NP because if it's possible to finish within some time period, then you can just show me that schedule as a certificate, and I can just check that everything finishes by that time. Okay, so that's an NP problem. Okay, so to show that it's NP-complete, we're going to reduce another NP-complete problem to this make-span problem. Okay, and that's going to show make-span is NP-complete. So the problem that we're going to reduce from is a subset sum. Okay, so remember that. So we talked about subset sum. So just to remind you, the problem is that you're given a set of numbers. Okay, so let's say 4 numbers, and you're also given a target value. Okay, and so this is a decision problem, and the question is there a subset of these values which adds up to your target? Okay, so in this case, if the target is 9, right, then there is a subset which adds up to 9. So for example, you can just take 9 itself, right? Or you can take 1 and 8, right? So there are different subsets which do add up to 9. So that's a yes instance of subset sum, right? But if you pick your target to be like 14, right, then you can see that there's no subset of S which adds up to 14. So therefore, this is a no instance. Okay. Yeah, and we actually proved that this problem is NP-complete. Okay, so if we can show that subset sum reduces to scheduling, then that would show that scheduling is also NP-complete. Okay, so to do this, let's let this be an instance of subset sum. Okay, so we have a set and we have a target. And also let's let little s be the sum of all of the elements in big S. Okay, so it's just the sum of all these values. Okay, so now we need to convert this subset sum instance to a scheduling instance, and that means that we need to create a set of jobs for the scheduling. Okay. And so the set of jobs we're going to create is just, we're going to take all the numbers in S, and we're going to create one job for each number. Okay, so for example, over here, right, we would just create 4 jobs. And the jobs have size just what the number is. Okay, so they have sizes 1, 3, 8, 9. Okay. And then we're going to add one more job. Okay, and this additional job, the size is going to be S minus 2t, where again, S is the sum of all of the elements in the set, right? And minus 2 times the target value. Okay. So we're going to assume that S is at least as large as 2t. Okay. So even with that assumption, subset sum is still NP-complete. Okay. Right. And so we're going to add this one more job over here. And now we're going to take all of these jobs, and we just want to schedule them on 2 processors. Okay. So even if you try to minimize make-span on 2 processors, which sounds quite easy, right? But that's still NP-complete. Okay. All right, and the reason is that so we can show this reduction of subset sum to make-span scheduling on 2 processors. Okay, using this set of jobs. And so the claim is that if you have a yes instance of subset sum, then the meaning that you have a subset of S which sums to t, right? Then the claim is that the make-span is going to be S minus t. Okay, and then later we're going to prove the reverse direction. Okay, but let's first prove that. First prove this direction. So the proof is simply that if you have a subset of S which sums up to T, right? So let's say this is a subset S prime. Okay. Then what we're going to do is we're just going to take S prime, right? And we're going to take all the jobs in S prime plus this one additional job, and we're going to put them onto processor 1. Okay. And so when is processor 1 going to finish? Okay. Well, it needs to do all the jobs in S prime, and all of them together, because they add up to T, right? They take T time to finish. Okay. And then it also needs to do this other job, which takes S minus 2T time. So the total amount of time that processor 1 needs is going to be S minus T. Okay. Right. And now what about processor 2? So processor 2 is just going to do all of the remaining jobs. Right. So the only remaining jobs are the jobs in S minus S prime. Right, because you put this extra job onto processor 1, so the only extra jobs are in S minus S prime. And the amount of time that these jobs take to finish is, well, this S, right, it takes S time to finish all the jobs in S. Okay, but T prime, right, the sum of all of these things is going to be T. So therefore, the time to finish all the jobs in S minus S prime is going to be S minus T. Okay. So that means that both processor 1 finishes at S minus T, and processor 2 also finishes at S minus T. And so since the makespan is just the largest finishing time, right, then our makespan is S minus T. Okay? Yeah, so this is one direction of the reduction. And now for the other direction, what we're going to claim is that if the minimum makespan is S minus T, okay, then there is a subset of S which adds up to T. Okay? And the reason is that, well, first of all, we have this extra job over here, and one of the two processors has to do it. Okay, so let's just assume that processor 1 does that extra job. All right, and then since the makespan is S minus T, okay, then, and since this processor 1 does this job, which is S minus 2T in size, then if you look at all of the other jobs that processor 1 does, okay, their size has to add up to S minus T, right, minus this extra job's size. Okay, and so that's just going to be T. And so that means that the other jobs that processor 1 does, they add up to T, right? But each of these jobs corresponds to an element in S. And so that means that there is a subset of S which adds up to T. Okay, so now we've shown both directions. We've shown that if there's a subset of S which adds up to T, right, this happens if and only if the makespan is S minus T. Okay? And of course, our reduction is polynomial time, and so that means that subset sum reduces to scheduling. And so even scheduling on 2 processors is NP complete. Okay, any questions about this? Okay, all right, so next we're going to look at an approximation algorithm for this makespan scheduling. Okay, so actually we're going to look at several algorithms. So the first one is the simplest algorithm, and this algorithm again is like very, very old. This comes from I think the 60s or something like that. Okay, so this is called Graham's list scheduling algorithm. Okay, so it's a very famous algorithm, and in fact, it's very easy to use. And even though it doesn't get a very good approximation factor theoretically, in practice it actually works very well. Okay, and there are many good properties about this algorithm. So in practice, this algorithm is used quite often. Okay, so the algorithm, so Graham's algorithm is basically a greedy algorithm. Okay, or it's not even greedy; it's just very simple. Okay, and so assume you have n tasks or n jobs and then m processors. Okay, and so the total runtime of Graham's algorithm is just basically all we need to do is to sort these tasks. Okay, and that's going to take n log n time. Okay, actually, I should add a m over here. Okay, and then you once you sort them, you don't sort them. Actually, in Graham's algorithm, you have to use something like a priority queue or something like that. Okay, and you have to use that n times, and so that's going to cost you n log n. Okay. And plus you need to look at all of these processors, so that's going to cost you m more time. Okay. So that's the running time. And so it's a very cheap running time. And if you compare this to like trying to find the optimal schedule, okay, then you would need something like this. Okay, so I'm not going to derive this, but basically it's some sort of exponential time if you want to try all possible schedules and then pick the best. Okay. All right, so the way that Graham's list scheduling works is, so the name says it all. So we're just going to list all of the jobs in any order, okay, any arbitrary order. And then as long as you haven't assigned all of the jobs to the processors, okay, as long as they're unfinished jobs, right, then if you ever see any processor which is not doing a job, right, so some processor finished all its assigned jobs and it's idle now, then you just take the next job from your list and then you give it to that processor. Okay, so that's the entire algorithm. Okay, just you list the jobs out in any order, and then you start giving them to processors, right? And then eventually the processors are going to finish the jobs they've been assigned. And once any processor finishes a job, you just give it the next job on the list until you've given out all the jobs. Okay, yeah, so as an example of this, suppose you have 3 processors, okay? And suppose you have a bunch of jobs and their lengths are like this, okay? Now, the first thing is that we can list these jobs in any order, okay? So let's just list them in some like arbitrary order like this, okay? And so initially, all of the processors don't have any jobs, okay? So therefore, we're just going to take the first 3 jobs in the list and we're going to give them to the 3 processors, okay, like this, okay? All right, and then next, we need to wait for one of these processors to become idle, okay? Now, the first processor to become idle is this P3 here, right? Because it's only got a job of size 3, so it's going to finish at time 3, okay? And as soon as it becomes idle, then you give it the next unassigned job, okay? Yeah, so you give it 2, okay? And then you keep waiting for the next processor to become idle. So this is going to happen at time 4 with this P1, okay? And then you just give it the next job on the list, which is 6. Right, and then you wait for the next idle processor. And so actually at time 5 over here, you're going to get 2 idle processors, okay? And so you just give them the next 2 jobs on the list, okay, like that, okay? And then in the end, your make span is just whoever finishes last, which is going to be P2. And so he takes 13 time units, okay? All right, so that's the algorithm. Right, so this turns out to be a 2 approximation algorithm, okay? But before we prove that, let me just first show you what the really bad case for this list scheduling is, okay? So when do you actually get like a 2 approximation, right? In which case do you actually get this bad performance, right? So the bad performance is, basically you have a bunch of small jobs, okay? So let's say that you have m processors and you have m squared small jobs with length 1, okay? And then you have one very big job, okay? All right, and now you're going to take all your jobs in list scheduling and you can list them in some arbitrary order. So suppose you happen to list all the small jobs and then the big jobs, big job, okay? All right. Then if you run list scheduling on the left over here, okay, then what's going to happen is that you're just going to assign these size 1 jobs like 1 by 1 to all your m processors, right? So here you have the processors, right? And then at time m, right, all of these small jobs are done. But then you have one big job left over and you have to give that to somebody. So let's say you give it to processor 1. Okay? So in that case, your make span is going to be 2 times m. Okay? And on the other hand, the optimal make span, okay, so the best way that you, so the optimal way to do this would actually be that you just take m minus 1 of these processors, okay, and you have them do the small jobs. Okay, and then for the final processor, you just give it that big job right at the beginning. Okay, and then if you do this, then at time m, right, you're basically you're done with almost all of the small jobs. Okay, there are only going to be m small jobs left at time m, and then you just give 1 to each of these m processors. Okay, and so in that case, your make span is going to be m plus 1. Okay. So list scheduling gets a make span of 2m, and the optimal one is m plus 1. So therefore, the approximation factor is something like 2. Okay. All right. So now, yeah. Okay. So now I need to do this proof. So I don't know if I can finish because we have like 5 minutes, right? Okay, well, anyways, I'll try to finish as much as I can, and I guess we have to continue with this next time. Okay, so we're going to prove that list scheduling is a 2 approximation. Okay, so let's assume that list scheduling gives you a makespan of m. Okay, and let's suppose that the shortest schedule has makespan m star. Okay, so we're going to prove that m is no more than 2 times m star. All right, so the way we're going to do this is let's look at the schedule produced by list scheduling. Okay, so suppose it looks like this. Okay, then we're going to focus on one task. Okay, we're going to focus on the task which finishes last. Okay, so let's call that x. Okay, so x is the job which determines the makespan. Right, so the makespan is going to be capital M over here, and x, because it's the job that finishes last, it's going to finish at time m. Okay, right, and now suppose x starts at time capital T. Okay, so capital T, it starts, and suppose the length of m is going to be little t. Okay, all right, so now we're going to prove some claims. So the first claim is that the optimal schedule, the optimal makespan, okay, that has to be at least little t. Okay? And the reason is simply that you've got this job of size x over here. Okay, you've got this job x of size t. Okay, and one of the processors has to do that job. Right? In any schedule, some processor has to do x, and so whichever processor does x, that processor needs to take at least little t time. Okay? And so that means that even the optimal schedule, right? Somebody does x, and so somebody finishes at least at little t time. So therefore, the optimal makespan is at least little t. Yeah. Okay, so next, we're going to prove that the optimal schedule is going to be at least capital T, right? The starting time for the final job. And the reason for this is because up until time capital T, okay, no processor is idle. Okay, now you see that after time t, you have some processors which can be idle. Okay, but before time t, capital T, right, no processor is ever idle. Okay, and the reason is because up until time capital T, you have at least one unfinished job, which is capital X, right? And so if let's say P1 became idle at this time point, okay, well then because you still have this X job left over, then you would simply give that job to P1. Okay? So if there's any processor which becomes idle before time big T, then that processor could be assigned some job, and then that processor would not be idle anymore. Okay? So up until when the final job starts, okay, no processor can be idle. Right. And so now that implies that, so now let's look at the total amount of work which is done by all of the processors up until time t. Okay, so what I mean by that is if you look at like the area over here, okay, so in each unit of time, each processor only does one unit of work, right? Because we assume all the processors have the same speed. Okay, and so since this entire area from 0 to t is filled up because no processor is idle, right? And you have m processors in total, then the amount of work in here is going to be at least m times big T. Okay, the total amount of work in that area. Okay. But that means that even in the optimal schedule, right, you need to take at least time big T, because the length of the optimal schedule has to be at least as large as the total amount of work you do divided by your number of processors. Right? Because if you have lots of work, then even if you completely evenly distribute that among your m processors, you need to take at least work divided by number of processors amount of time. Okay? And we know that our work is going to be at least m times t, and so therefore even the length of the optimal schedule has to be at least capital T. Okay. All right. So therefore we have these two claims. Right, so m is going to be at least m star is at least the size of the big job, the final job, right, and at least as large as the starting point of the final job, and so that means that the optimal makespan is at least as large as the maximum of these two quantities. Okay, right, and now what about our makespan? Okay, our makespan for list scheduling is simply capital T plus little t, right? M, that's what it is. Okay, because X is the last job to finish. And so therefore our approximation ratio, which is m divided by m star, right, that's going to be no more than than m divided by the maximum of big T and little t, right? And this is always going to be at most 2. Okay, if you add 2 numbers and then you divide by their max, that's no more than 2. Okay, and so this shows that list scheduling is a 2 approximation. Okay, any questions about this algorithm or the proof? Okay, so yeah, so there's a bit more I'm going to say about this. So we're going to look at sort of a variation on list scheduling, which gets a better approximation ratio. Okay, yeah. So and then in fact, there's another scheduling problem I want to talk about in the next lecture. Okay, yeah. So next lecture is on Thursday. So everybody, please make sure you attend the lecture. Okay.